All right, so what we're doing today, here's the essential understanding. Some real-world problems involve multiple linear relationships. What we've been working with are simply two of them. It was two lines, and we figured out what they cross, shade above, shade below, all that good stuff, and we found a region that had a bunch of answers in it, right? So it was where all the shades were at. Linear programming accounts for all of these linear relationships and gives a solution to a problem. So with linear programming, you're not working with one or two equations that you shade above, shade below, but a whole system of them. Sometimes 3, sometimes 4, sometimes 5, depending on how many models that you have. So that's what we're going to be doing today. This fancy thing called linear programming. We're not going to sit there and type in code. That's just what it's called. So we're not working Java or C++ or anything like that. Here's what you do need to know. And this is kind of funky, but I'll explain to you a little bit. The objective today. There is a minimum, if there is a minimum or maximum to a system, or a linear objective function, it occurs at one or more of the vertices in the feasible region. But, did somebody understand that? Want to say that a better way? Okay, here's what it's saying. Think back to the systems of inequalities. Let's say this is one line right here. And then we had to shade above or below, right? Let's make this up here. Let's go shade below this. Cool? And let's say I had another function, and there's the other one. And when I figured out to shade that one, I also had to shade below. So when I shade below that line, okay, notice there's three different solutions, right? There's one here. Is that the solution to the system? No. No. Is this over here the solution to the system? No. But in here there is, right? That's what you're calling the feasible region. That means everything inside of there could be the solution if you wanted it to be. It would make the statement true. Now I want you to notice that those two lines cross at one point, correct? And that point is right here. That is the vertex of this system if we had to solve it. That's the vertex. So what they're saying is, if we're looking for a minimum or a maximum, it has to happen at one of the corners, one of the vertices of the feasible region. Let's be a little bit more specific, because right now this is kind of vague, but I'm going to show you exactly what it looks like. So let's take a look here. We have this function here. I'll write it nice and big for you. It says P is equal to 2x plus y. And what we're trying to do for this one, please put those pencils down and watch. I'll let you copy to your heart's content. We got plenty of time today. And it's really not that difficult where you want to write everything step by step, sorry. So there's my function, P equals 2x plus y. Now, what we're working with are business models, okay? And I got to see those in practice when I was working at Mickey D's. I don't know if you guys knew, but I worked there from like my junior year all the way up to I graduated college first time. Got me through. It was awesome. It got this body too. So great. But anyways, here's something that was really interesting that I learned in McDonald's, because you know I was going to, I don't know if you guys know, but McDonald's actually has their own university. Did you guys know that? Yeah, you might laugh, but there's people that make a living out of it, and they make some serious money. They become store managers, and we won't talk about how much money I made, but I actually took a pay cut to come be a teacher, which was sad. But anyways, when you're doing these courses with them, you know how you always see, come get the McRib for a limited time. Do this for a limited time, limited time, limited time. Everyone's seen that, right? And that's really interesting. I'm like, why is it limited time if you're making money off of it? Well, the truth is that when they first start a sale, anywhere, whether it's fries, any business, at the beginning they're not making money. Okay? When you take home your 1 pound of strawberries for 99 cents, they're not making money. But if they sell enough of them, they are making money. They get to a point where they break even first, and they're like, all right, it wasn't a total fail. But then they start making money, 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 money. And then they get to a point where it's like the most money they'll ever make. Because then at some point, if they keep selling, they start losing money on it. Which is really interesting, because I never thought about that. Like, can you sell so much that you're not making enough money? And yeah, that's pretty interesting. If you think about it, let's say if we are at McDonald's, and let's say you've got like a lot of people that are ordering all these burgers. Okay? What happens is you're going to need more people to make them, right? Which means you're going to have to pay those people. So if you're selling a lot more than what you can handle, or that sweet spot, then you're hiring more people, which means you're spending more. And is that 99-cent McChicken really going to make enough to pay that one person for an hour labor? No. So sometimes that's why you see they don't hire enough people. But what happens when you're waiting in line? You wait there for like 5-10 minutes, right? Because that's where those functions or those equations are in conflict with each other. Okay, they're not in that optimal point. But anyways, that's just way too much. We want to maximize this function. Let's pretend that this is profit for now. Okay, and they have all these different constraints that we do have to think about. And these are the constraints. So maybe one of them is how much labor I've got, how much investment do I have, how much product am I selling, and how much is actually leaving the store. Okay, so think about them that way. They're just different scenarios that are that are beyond our control, that we kind of have to put into that. So here's what I'm going to do. I'm going to graph this, and I'm going to find that feasible region where I'm kind of making money. So I'm going to use Desmos. That's probably the easiest thing to do. Where'd you go? Let's close this. Let's get rid of that. Let's get rid of that. Let's get rid of some ink here. So here's what you got for Desmos. Let me ask you guys a question real quick. What does this function here mean? Y is greater than or equal to 0. If I'm going to graph that, huh?
Y can't be 0.
Yeah, all it's saying is that all my solution, and I'll graph it so you guys can see it. And the reason is because I don't really want to have them there with everything, but here it is. Y is greater than or equal to 0. Where's 0? 0, 0. See that? That's just saying that my answers can't be below that x-axis, x-axis. Does that make sense, everyone? Now, the other one says x is greater than 0. So if I type that one in, x is greater than equal to 0, and then I got that. So what this is telling me is that all my answers are going to be in quadrant 1, correct? Does anyone see that? Cool beans. So I don't want to have them there because it's going to get really nasty, really messy real quick. But I know that these are all my answers in here, but I am going to graph the other two constraints. The first one says x plus, oh, come back. Baby, come back. X plus 2y is less than or equal to? Less than or equal to 5. So less than or equal to 5, there's one of them. And the other one says x minus y less than 2. So x minus y less than or equal to 2. Oh, that's gross. Can we get another color in there? Let me close this and do it again. I know. X minus 2y. Or was it? No, it was x minus y, huh? X minus y less than or equal to 2?
Yeah.
That's better. That's way better, huh? All right, cool. So if all my answers were in quadrant 1, then that means that my solutions are from here to here, and then here, and then finally, no, not finally. Oh, where'd it go? Here we go. Here, and so that little quadrilateral is a feasible region. Everything inside of here is technically an answer to the system, right? But the question is, we want to maximize. We want to maximize. We want to get the most bang for our buck. And that definition that we had earlier is saying that the max happens at one of those vertices. A max or minimum will always happen at the vertices. So what is a vertex? Anybody remember that? It's a corner. It's a corner. So this corner right here is at 0, 0. And then this one right here is at, what is that, 2, 0? And then I've got another one over at 3, 1. And the one up here is at 0, and it's not 2, because here's 2. It's 2.5. 2.5. So if I'm going to have a max, it's going to happen somewhere here. Does that make sense? I want to pause here and do a thumbs up, thumbs down if you're good so far. We're okay with what we're doing. And all we're finding are some possible things here where it can be true, okay? So, everyone got those written down? Please take a second and write those down because I'm going to forget what they are. I've got sunshine on a cloudy day. When it's cold outside. say? No, I was going to, but then I graduated and I quit. It's like, but you know, I really thought about it, like, should I wait till I quit and then go to, it's called Hamburger University. It really is, it's HU. Yeah, it's called Hamburger University, and you do all these courses, and they kind of teach you to run a store, but man, they make some money. So I wouldn't be clowning that, guys. If like you're serious about making some, like, I'm talking about like anywhere from 75 starting, 75,000 a year. Yeah, at McDonald's.
How long does it take? I'll be a grad trying.
It just depends. It just depends on how hard you're willing to work. Yeah. When I was there, the store manager made 110,000, and this is like, well, hold on. This was years ago when I was in school. I mean, I'm sure she's making more now, but she was making 110,000 plus bonuses. So at the end of every month, she would get a bonus on top of that. Like if the store did well, here's a certain percent. Here's your cut.
As a manager?
She was the store manager, so she ran the whole store. So if the store bombed, her money also went down. But yeah, you'd be surprised. You'd be surprised. Many weird things. But we're not going to talk about that right now. Yeah. Well, I mean, it depends. I mean, some people, we'll talk about that later. Let's get this program out of the way. You guys got that? All right, cool. So here's my function. I'm going to put the constraints away. I'm not worried about those already. I've already graphed those. Thank you. Welcome back. Thank you. So I put the constraints aside because I've already graphed. I've got what I need, which is the vertices, correct? Now, I need to check those vertices. What were they again? I remember 0, 0. 2, 0. 3, 1. 0, 2.5. So, here's what I'm going to do. I'm just going to plug them in. So, if this is 2 times 0 plus 0, that's going to give me 0, doesn't it? It's 0 plus 0, 0. 0 plus 0 equals 0. So, this gives me a 0. If I plug in the next one, it's going to be 2 times 2 plus 0. 4 plus 0 equals 4. So this gives me a 4 there. Let's try the next one. 3, 1. So 3, 1. Sorry, just kidding. 2 times 3 plus 1. 6 plus 1 gives me 7. So this gives me a 7 value. And then I'll do the last one over here. That is 0. So 2 times 0 plus 2.5. 0 plus 2.5 is 2.5. So take a look here. These are all of the vertices. Magic question. Where does the max? Where can I maximize profit at? 3, 1. Can you guys see that? This is where I maximize profit. And what that could mean is, if I want to maximize profit, maybe I only want 3 employees. You see how that works? You got X and Y. Maybe I only want to hire 3 employees and maybe pay them blah amount of money, whatever that one represents. Okay? So X and Y would represent those things. And each function would mean its own thing. But if I want to maximize profit, I want to make sure that I'd be at 3, 1. Which, as far as the picture's concerned, where'd it go? Did I close it? What? To do what? Yeah, you'd have to check it. That's, I mean, well, how else could you do it? Oh, that was great. Well, you know what? Sometimes you can eliminate some of them. Obviously, right? This 0, 0 obviously going to be is it going to be a maximum? No. But I don't know about the other 3 points. Okay, because maybe I want to hire no employees and pay them very little, or I want to, and this should make sense. I want to hire more employees, pay them less. I could get money that way because I'm not dishing money out in salaries. Or I can hire very few of them, pay them a lot. And it's known that if you pay employees well, they perform better, don't they? But I don't want either one of those because that's not optimal, is it? So I want to get a few more workers and pay them a decent amount of money. See how that works? So all of that should kind of go, it kind of explains itself in the end. And right now what we're worried about is how do I maximize, minimize stuff. We're not worried about all the details of it, but how can I maximize, minimize? What's up? Thursday. Okay. So if we're talking about that function actually being how much we're paying people, think about this. If I want to minimize the cost on how much I pay people, how many workers should I have? If I want to minimize my cost in employees, how many employees should I have? And what should I pay them? Doesn't that make sense? Yeah. All right, cool. We'll get to that. Yeah, you can do that. You'll get time. Here's a new function. What's up?
Can I write the constraints for that one?
You want that?
Yeah.
Hold on. Let me. Let's do this. Here's your constraints.
Thank you.
Can you see it now?
The answer is just 3-1.
Yes, but you guys have been doing all right today.
Yeah, we haven't even said it.
I know. Hey, I don't think because you're too busy munching on those Cheetos.
No, that's because he's mad.
Go like this. Not you. You just got caught red-handed. Red finger. SMH. Shaking my head. Quiet down. Yeah. Actually, let me do this real quick. How's that? Better? They put MRSA. Way too loud. So that means that you guys are done. All right, check this out. What? Okay, we'll do that in a second. That way I can put people to work. Guys, same constraints, which means same coordinates. All I want you to do now is maximize this function up here. P equals x plus 3y. So don't go back and graph it again unless you want that practice. All we're doing is maximizing again. Same constraints, which means same vertices, right? Maximize that for me, please. What?
So we're just putting it into that equation.
You can, but if you do all of them, you're gonna want to be careful where it is. Keep tracking it because it gets really messy, especially when they throw that black on there. But so be careful with that, okay? But yeah, ideally you want to graph all of them, but because these last two, I know it just means in here. Right, I graphed the other ones and just remember that my answer is going to be that shaded part there.
Hold on, go back.
Make sense? So there are your vertices. Thank you. Thank you. Give me a second, okay? Thank you. There's your vertices. Who figured the max here? What was the maximum? Sean?
Wait, maximum?
Yeah, but which one produced the maximum?
3.1.
3 comma 1? Was that the maximum?
Oh.
What did this produce?
Oh.
What was it?
I did it the wrong
11.5?
I did it 3N, so okay.
What was this then?
Wrong.
6?
I did it the wrong one, yeah.
But you see what happened, right? Alright, cool. So, questions, thumbs up, thumbs down. Are we good here? Yay! Alright, cool. We're done.
Let's go.
Guys, there is homework already open for you.